is Laura Nuttall from Portsmouth, who's an expert on gravitational waves. So Laura did her PhD at Cardiff and then moved to the US to take up a couple of postdoc positions at Wisconsin and then at Syracuse before returning to the UK and Cardiff again for a research fellowship, and is now at Portsmouth, where she's a Future Leaders Fellow and lecturer. And today she'll be talking to us about current and future prospects in gravitational wave detection and astrophysics. So Laura, thank you very much for agreeing to virtually come and speak with us, and whenever you're ready.
Thanks very much, and thanks everyone for joining this afternoon to hear about gravitational waves. It's a very exciting time to be in this area of astrophysics, and it was even more delightful that the catalogue, the second catalogue, came out yesterday, so I get to talk about all the exciting things that we've been doing over the last few months. So yes, this is going to be a whirlwind tour of gravitational waves, what they are, how the LIGO detectors work, as well as what we've been recently finding out. So without further ado, when we think about gravity, we might start with thinking about Newtonian gravity, what we learn in school. And what we learn in school is that gravity is a force. It acts instantaneously over a distance, and that every particle attracts every other particle in the universe with some force. And that's a nice ideal view of gravity, and it works for the majority of our life here on Earth, where we're not moving at particularly relativistic speeds, where gravity isn't particularly large. And it's nice to think of a jolly old gentleman sat underneath an apple tree with an apple falling on his head and going, oh wow, that's gravity. But what we actually find is what Newton says about gravity starts to break down when we go out there into the universe, or even when we just look at our old solar system. In this video here, what you're seeing is the orbits of the planets around the sun. And if Newtonian gravity were thoroughly correct, when we take away the sun, the planets immediately, if you like, know that the sun has disappeared and then carry on in the direction of travel that they were taking. If you like, there wasn't any time for them to realize, if you like, that gravity had disappeared. And that's not the view that we know should happen. If you like, it takes time to realize that gravity has disappeared. And so, if you like, there's various different ways as well that we know that Newtonian gravity isn't sufficient, such as, if you like, GPS, and we need to understand Einsteinian gravity to understand orbits and various things like that. But I always like this picture. And so we have to go on to look at what Einstein says about gravity to understand it in more detail. And for that, we need to consider something called space-time. And so this is the X, Y, Z direction combined with time. It's supposed to be it is a four-dimensional thing in some respects, and I certainly can't think of that many dimensions. So I much prefer to think of space-time as, say, a trampoline or a rubber sheet. And in this scenario, I like to think about all the properties that this rubber sheet or trampoline might have. If you put, say, a tennis ball on the trampoline trampoline will bend ever so slightly around the mass of the tennis ball. Not a great deal, there's not a lot of it there. But if you replace it with, say, a football or a ball with which is heavier, more mass, then the trampoline will bend even more around that object. And this is a really nice idea to think about how space-time is actually behaving around objects. If you like, the more massive an object is, the more space-time will curve around it. And so in this scenario here, what we're kind of seeing is, if you like, the yellow ball being represented by the sun, the bronzy coloured by, say, the Earth, and the red can be the moon, for instance. And what we see is the more massive an object is, the more that space-time is curving around it. And in this scenario, we just need to remember that gravity is the curvature of space-time. That's all it is, this geometrical property. And the more massive an object is, the more it will cause space-time to bend, and the stronger gravity will actually be. And so then we can start thinking about gravitational waves, now that we understand that, if you like, we all exist in this four-dimensional web of space-time that is bendable. Now, whenever a massive object moves or accelerates within space-time, it causes the curvature of space-time to bend. Me running for the bus, me waving my arms right now, you at the screen, I am causing space-time to bend around myself. And what I'm doing is I will be sending ripples out into space-time. And these are in the form of gravitational waves. These ripples travel at the speed of light away from the source, carrying energy with them. And it's a nice way to think about it in a similar analogy to a boat moving through water. As the boat moves through water, ripples emanate, say, away from the very front of the boat. And it's the exact same thing that happens here when an object is moving through space-time, accelerating, or it has to be asymmetric as well, then it will produce ripples in the fabric of space-time. So as I mentioned, anything with mass will do this. So why aren't we detecting gravitational waves all the time? Well, we're actually having to wait for nature to actually give us detectable gravitational waves in the form of collisions of neutron stars and black holes to the cores of dead stars. We need them to be colliding to, if you like, emit strong enough gravitational waves that we have the chance of actually detecting here on Earth. So what you're seeing here in this animation on the bottom right is a computer simulation of the very first detection we made back in 2015 of two black holes inspiraling. I think it's something like their last 7 or 8 orbits. And then up on the left-hand side, you're seeing a very exaggerated view of how the Earth will stretch and squeeze in response to the passage of these gravitational waves after they have spread throughout the universe. And gravitational waves will actually cause a stretching and squeezing, like the video showing here of the Earth. Now, if you imagine a gravitational wave coming in or out of the screen right now, it's going to cause a ring of test particles to stretch and squeeze in this manner, in kind of like a plus configuration, just like you're seeing. So it's passing through us all the time and causing all of these stretching and squeezing. But gravitational waves are extremely, extremely weak, and they attenuate with distance. So we have to wait for nature. We cannot create detectable gravitational waves here on Earth, at least not yet, let's say. So how do we go about detecting these gravitational waves? Well, we need to use massive interferometers, and this is where the LIGO experiments come in. So LIGO stands for the Laser Interferometer Gravitational Wave Observatory, and there are 2 located in the United States. One in Hanford, Washington, and the other in Livingston, Louisiana, some 3,000 kilometers apart. And if you Google these instruments, you'll happily see these massive L shapes stamped into the Earth on Google Maps. So these interferometers are designed to take advantage of this stretching and squeezing nature that I was just mentioning on the previous slide. But what you can see here with the LIGO detectors is, even though they might be twins, they've been assembled in environments that are extremely different to each other. Hanford being up there in the desert, in the Washington desert, nice tumbleweeds, nice mountains there in the background, and Livingston on the right here is in the swamp there. So the characteristics, if you like, of the noise of the detectors is very much influenced by its environment, and that's something to always bear in mind. Now, each of these arms of these LIGO instruments are 4 kilometers long, and they need to be this long to be able to have any hope of detecting the collisions of black holes and neutron stars. Now, just to put that into perspective in relation to, say, where, well, maybe not where you are right now, but where you would usually be in work, if I shoved a LIGO in the center of London with one end starting at your university building, that is roughly the full length of how a LIGO would, if you like, shape or get in the way of central London just there. So you need to have a lot of area where there's not much going on, not much traffic, not many people, all those types of things in order to be able to do gravitational wave experiments. So now let's have a quick look at roughly how this interferometer actually works. So our telescopes are very different to, if you like, what you might consider a typical astronomical instrument, and that's absolutely fine. Electromagnetic telescopes typically, if you like, point at a certain region of the sky and intake information like that. Instead, we're a massive microphone. We're listening to gravitational waves coming from anywhere in the universe. We're just trying to pick them up. And so, like I said, the stretching and squeezing nature of space-time nicely blends into the L shape of our interferometers. So on the far left-hand side there, we have a nice laser source, and here's a picture of our laser system, of part of our laser system anyway. And we shine this light towards an optic called the beam splitter. Now, this beam splitter is at a 45-degree angle, and it does exactly what it says on the tin. It splits the beam into 2. We then send the beam up one arm, and let's go with the Y arm here, going right to the vertical top of your screens here, where it's going to end up hitting a test mass. So I've just put the pictures up here. So these test masses are are hung on fused silica fibers. That's what the top left-hand image is showing there. And we're doing this so that we can isolate them as much as we can from the background. As well, the test masses, as you can see here on the bottom right-hand side, are in a 4-stage pendula, again, to try and reduce seismic noise. So the light is, say, bouncing up the y-arm and up along the x-arm to these end test masses. They're going to bounce off these end test masses after a travel time, well, after going 4 kilometers. They're then going to travel back to the beam splitter and then recombine. And hopefully we can read a signal out just there. So what you're actually going to be thinking is, okay, there's a few more optics that you've actually not described in this picture, and it's best not to really focus on too much about that. These, if you like, are some of the main ingredients of a LIGO interferometer, and there's a lot more bells and whistles that I'm not actually showing. But the main principle here is that we are a great big timing experiment. So as the laser light is traveling backwards and forwards in the arms, if a gravitational wave comes by, nothing happens. We don't see anything down there at the photodetector. But if a gravitational wave happens to have come by, what will happen is it may stretch the y-arm and squeeze the x-arm simultaneously. And then as the wave passes through the Earth, passes through the experiment, the interferometer, it's then going to squeeze the y-arm and lengthen the x-arm. So as the light is bouncing backwards and forwards in these arms, it's actually going to be phase shifted. And so that's what we're actually detecting there at the bottom of the photodetector. Another way to think about it is, instead of thinking of light, think about 2 rows of soldiers marching perfectly in time. The 2 lines of soldiers leave the laser source, and once they encounter the beam splitter, they split up. One line of soldiers goes up the y-arm, the other line of soldiers goes down the x-arm. They turn around at the end test mass and come back, and they recombine there at the beam splitter. Now, if they've both traveled 4 kilometers, they'll still be marching perfectly in time. However, if a gravitational wave happens to have come by and, say, stretched the y-arm, that line of soldiers will have marched a slightly further distance. And likewise, in the x-arm, they'll have traveled, if you like, a slightly smaller distance. So that by the time they come back and reach up, they'll be marching slightly out of time. And that's exactly what we're looking for. We're looking for the phase difference in the 2 beams of laser light. And with that, we can then tell a gravitational wave comes by, and more importantly, what type of gravitational wave, what kind of event actually produced it. So what we're seeing as another picture that popped up here on the top right is just another image of our wonderful test masses there that is glowing nicely from one of our commissioners, having just assembled it, and is looking to make sure there's no smudges from their fingers, from their thumbprints and things like that on the mirrors. These experiments are extremely sensitive, so that is enough to really set us back, let's say. And that's because we're detecting gravitational waves that will stretch and squeeze our arms on the order of 10 to the minus 18 meters, which is a crazy, stupid small size. Come on. Oh, I seem to have. Nope, here we go, back again. So let's just think about what that actually means, 10 to the minus 18 meters. A penny is something like 10 to the minus 2 meters. Diameter of a hair, 10 to the minus 5. Width of a DNA molecule, 10 to the minus 9. Size of a proton, 10 to the minus 15. And we're trying to detect 1,000 times smaller than that. Gravitational waves will stretch and squeeze, if you like, by a length smaller than the smallest building blocks that are made up in your body. So that's why there's no chance of you feeling, if you like, gravitational waves kind of coming at us right now from all the collisions of black holes and neutron stars out there, and why we've got no chance of really detecting them if we made them here on Earth. We're purely at the mercy of nature, and we've actually been extremely lucky so far. And so just to tell you a bit about the global network here, I mentioned the LIGO detectors there in the US, Hanford and Livingston. We also have the Virgo detector, which is a 3-kilometer interferometer near Pisa in Italy. The GR600 experiment is much more of a prototype placement where we test out a lot of the infrastructure for the advanced LIGO detectors. And we also have the CAGRA experiment that actually came online earlier this year to join us at the very back end of our latest science run. And that's another 3-kilometer interferometer, but this one is in the Kamiokande mine underground. The rest of the interferometers are above ground. LIGO India is in the pipeline right now to be built. I'm going to guess it's something along the lines of 5 years away, something like that. So it's not been online recently, but will be in the, I guess, not too distant future. But just to give you a bit of an idea, this is, if you like, the global network right now of where all the different interferometers are. And that's mainly so that we can all work together. We're all working together. We're not working in competition. Because these signals are so weak, we want to be able to detect them at multiple places on the Earth to not only help with sky localization, but also to help with confidence, with definitely making sure we've seen something. 10 to the minus 18 meters, you know, I can jump up and down next to one of the main benches of the interferometer and cause it to move by more than that. So, you know, we need to definitely ensure that it's come from something astrophysical. So I want to move now on to, if you like, detection of gravitational waves. And I'm really just going to focus today on transient sources. Transient sources being gravitational waves that are transient in nature. They're coming through the Earth, stretching and squeezing us on the order of fractions of a second to minutes. Now, at the moment, we've only detected transient signals from the collisions of black holes and neutron stars. Now, that's not to say there aren't more sources out there. It's just that the detectors were designed to detect these things. So I'm going to be talking, if you like, about some techniques to find these signals, which are to do with match filtering. So match filtering is where we, if you like, know roughly what the signal is that we're looking for, and we're going to go and search for that in our data. So what you can see in this animation is on the bottom here, is you can see in the black some of the LIGO data from the LIGO Hanford Observatory, where the data has been whitened and bandpassed. And the purpley pink line there is showing you a gravitational wave template. So we've taken Einstein's equations, we've solved them for, say, two binary black holes merging, and that's the signal that we expect to be able to see in our interferometer. So with match filtering, we take advantage of the fact that we know roughly what the signal should look like, and we brute force that and look for that in our data. And so what we do is that every iteration of the data, we can then, if you like, produce a signal to noise ratio time series that you're seeing here on the top of the animation. And so you can see here nicely that there's nothing really much lining up with what the signal might actually look like. But when we actually do find something in the data that looks like the signal, you'll see a peak in the signal to noise ratio time series to say, aha, we think there's a gravitational wave there at that time in the LIGO Hanford interferometer. We then look for the exact same signal in LIGO Livingston, and as long as they occur within the same light travel time, i.e. within 10 milliseconds, we know that it should be due to a gravitational wave rather than, say, something environmental. Same with Virgo. Virgo's more on the order of 30 milliseconds away. So the more interferometers you have, the more you can check for these coincidences and check that the signal looks like what you're expecting. And so we do this in a multiple number of different ways to try and find gravitational waves. One way in which we can look for gravitational waves is using externally triggered source searches. So in this manner, we take, say, Fermi or Swift, some would say a gamma ray burst monitor, and they tell us, right, we've seen a gamma ray burst at that part of the sky at this time. And then we can go, okay, thanks for that. We'll then go and look in our data at that time, roughly knowing where on the sky it should have come from, and try to see if we find gravitational waves associated with that event. There's nothing that we've detected so far like that, but that's one way in which we can do it. Another way in which we search for gravitational waves is what we call in low latency. We use similar methods to what I was just describing with the match filtering, but we try to search for it in close to real time, so that if a gravitational wave goes through the interferometers, we know within a couple of minutes that that was actually the case. And the whole point of this is to then alert the rest of the astronomical community so they can point electromagnetic telescopes and find the electromagnetic counterparts should there be one. This worked to great effect with GW190814. So this was back in 2017 when we detected the collision of two binary neutron stars. We told the astronomical community to go and look at a certain part of the sky, and there, lo and behold, was the kilonova signature as well as the afterglow signatures. We want more of that. We want much, much more of that. Hence why we do this form of search, low latency. But we also have a high latency search, and this is where we take data containing weeks amounts of our data, and then we go and search for gravitational waves within it. Now you might be thinking, well, why do that? You've already got the low latency search. And that's because we can fold in extra information, such as data quality information, calibration information, and we can actually use some slightly better, well, more advanced techniques, let's say, built upon match filtering techniques to search deeper in our data. So if you like, the low latency searches will, if you like, find the loudest events, but by using the high latency searches, we can dig deeper into our data set and actually find all of those pesky gravitational waves that are actually lurking much more close to threshold. So it's very much worth doing both of these forms of searches. And so then this nicely leads on to the second gravitational wave transient catalogue, which we published just yesterday. So this seminar came at a very fortuitous time for me to chat about it. So the second gravitational wave catalogue comprises all of the first, the second, and the first half of the third observing run. The third observing run being, well, the first half of the observing run being O3A, and that concluded in October last year. So it's taken us about a year to be able to, if you like, look through all of our data and actually tell you all about it. So just to kind of give you a bit of an idea, like, so the first observing run was about 3-4 months long back in, which concluded in the beginning of 2016. And at that point, the interferometers were, where we just turned on the interferometers in the since we've done some massive upgrades that took on the order of 5 years. Now, on the bottom left there, it's hopefully giving you a bit of an idea about the sensitivity of the detectors and their evolution throughout the last, 5 years. So on the X is the different interferometers, and on the Y there is a measure of sensitivity that we use called the binary neutron star range. Now, the binary neutron star range is, if you like, the average range at which we can detect a binary neutron star at threshold. Average, not furthest. Depending on where the signal comes from on the sky, the detectors are slightly more sensitive. Slightly more sensitive if you're below or above a LIGO, let's say, and less sensitive if you're coming at it from an angle. So this is the average. Now, what you can see in 01 was that Hanford was a little bit more sensitive than Livingston. This is the pinky kind of block that I'm showing you here, where Hanford was around 75 and Livingston around 65 megaparsecs. Okay. You have to forgive me for just kind of shimmying in what the 01 sensitivities were. Virgo was not on in the first observing run, hence why you're only seeing the 2 LIGO sensitivities here. Now, we went offline for something like, what was it, about 8 months, did some upgrades, and then we came back in the second observing run, which is shown there in either the light blue, the light red, or the light purple. And here what you can see is that the Livingston detector actually got more sensitive, but the sensitivity of Hanford went down ever so slightly. And this is because what we were concentrating on doing is trying to upgrade the laser power to try and increase sensitivity. It didn't particularly do that, and unfortunately we realized that there was something not quite right with one of our end test masses, which actually introduced some form of noise which we call jitter noise. Too much shaking basically of the mirrors, and so that decreased sensitivity. As well, Hanford unfortunately suffered a massive earthquake in Montana, so that isn't very far from Washington State, and that also affected the alignment of the interferometer right towards the end of the second observing run. So not great, but never mind. And Virgo came on for the very first time towards the end of that observing run as well. Now, O3A, we had a much further break between the second and third observing run where even more upgrades were done. And in that observing run, the detectors came back online with much, much more increased sensitivities. Livingston being around 130, 140, Hanford something like 110 megaparsecs, and Virgo coming up for 50 megaparsecs. Now, we split the run into 2 halves, O3A and O3B. We're still analysing O3B, but we've analysed all of O3A, and there isn't that much difference in terms of sensitivity between O3A and O3B. Now, what did we find? So in the low latency searches, we found 33, or what we suspected was 33 gravitational wave events in O3A. However, 7 of those we retracted. We realized there were some things not quite right with how we'd actually said that these were gravitational waves. The data might have been glitchy, various things. But we also did our high latency searches and found an additional 13 signals. So that included if you like, 39 events that we found in O3A. So when you combine this with what we'd previously found, 3 events in O1 and 8 events in O2, we now stand at 50 gravitational wave events that we have seen so far. And like I said, O3B is yet to come. You're going to have to unfortunately wait a few more months for that. So I'm going to spend the rest of the seminar talking about what we're actually learning from all of our events. What are some of the exciting things that we're seeing? And I love this plot. Okay, so this is actually showing you, if you like, all of our events that we have seen so far. The x-axis isn't showing anything at all, just a separation. And on the y there is solar masses. So, so what you can see here is that in the blue are all of the LIGO and Virgo binary black hole mergers that we have detected so far. Okay. In purple is, if you like, a comparison of how black hole masses compare when we've detected them electromagnetically. When I say we, not me, others in the astronomical community. In yellow is all of the neutron star masses that have been detected through electromagnetic means. And in orange there are the neutron stars that we, LIGO and Virgo, have detected. So what you can see here is just an absolute plethora of black holes and a few things lurking around at the lower mass area, just down there at the bottom. Now, if I said to you, right, where's the very first detection? Where's the detection that, if you like, shook up astrophysics and earned a Nobel Prize from the in physics for the first detection? It's actually that one. It's nicely buried there in the population now. It looks very typical, if you like, of the bread and butter black holes that LIGO and Virgo are seeing all of the time. I had to really, really stare and actually find it myself. So that's really quite nice just to, if you like, be able to see what's happened in the last 5 years. And so let's have a quick tour of some of the most interesting events that we've seen in the 3rd observing run. So what's the most interesting things that we saw between, what was it, April 2019 to October 2019? I'm going to start with this one here, the heaviest system that we've seen, GW190814 So GW190814 seen on the 21st of May 2019. And what we found is it was a binary black hole collision where the primary and secondary mass of the compact objects are listed here. The first object being somewhere between 74 and 121 solar masses, and the second object between about 46 and 88 solar masses. Now, what's really quite exciting is, well, there's a few exciting things about this event, but one of the exciting things is that the collision of these 2 objects produced a black hole of about 150 solar masses. So this is one of the first times, sorry, this is the first time we've been able to say we've seen an intermediate mass black hole. So that was really very exciting. On the right-hand side, what you're seeing is, if you like, spectrograms of the data for this event. Blink and you'll miss it. On the x-axis is the time in seconds, and on the y is frequency, and it's colored by, I'm going to guess the amplitude spectral density of each interferometer. So what you can see here is this signal is fractions, absolute fractions of a second, 0.1, 0.2 seconds in length. And that's purely just because of how much it actually appears in our sensitivity region. The heavier you go, the shorter the signals are because they merge at lower frequencies. And we don't tend to look at the moment below about 20 hertz, something like that. So this is on the edge of, if you like, seeing the final inspiral and merger that's within our sensitivity band. Another really interesting thing about this object is when you look at that primary mass of that first compact object, that's sitting nicely in the region of the black hole mass spectrum. The gap in the upper gap in the black hole mass spectrum. So right now, stellar evolution says that you cannot collapse a massive star and create a black hole with the black hole having a mass between about 65 and 120 solar masses. And this is due to a phenomenon called pair instability. So this is a point when a star becomes so dense that it creates electron-positron pairs within its core. And when this happens, it produces a sudden drop in pressure and the star effectively implodes, ripping apart the star, producing absolutely no remnant of any kind. So we've seen something within that region. What does it mean? Does it mean that maybe our understanding of stellar evolution isn't quite right and that you can actually produce high mass black holes? Or is it that the black holes that we saw, did they result from a previous merger? So that one seems quite likely, given that all of the black holes that we've seen so far are producing, if you like, a remnant black hole that might be within the 70 to around, say, the 70 solar mass region, so well within the mass gap region. So the multiple merger scenario is quite plausible, but it does require that this system was formed in a very dense environment, i.e., however many eons ago, two black holes came together to create the first remnant, so the primary mass of the one of the compact objects. And then there's been enough time for another black hole to come along, be bound within that system, in spiral, and merge to create the system that we have seen here. So that's really exciting because we haven't really started seeing anything like that before. I'm not saying the data definitely supports that. We're not quite sure just yet, but it's certainly a plausible scenario, and that's why this one's really quite exciting. Going back to our beautiful array of black holes, let's now look at this one, GW190814. Yeah, 14, that's right. So what you can see with this event, just looking at this plot, is that the masses of the compact objects that merged were really asymmetric. They were really very different. So with this scenario, with this object, what we saw is that we saw something like a 23 solar mass object collided with something that was about 2.5 solar masses. Now the question where everyone wants to know, that secondary object, is it a really heavy neutron star or is it a really light black hole? Both are extremely exciting because it lands within the lower mass gap of black holes, somewhere between what we expect neutron stars and black hole masses to be. So we tried looking to see if we could actually discern that. And one way in which we can look to see if that was definitely, say, a neutron star is looking for tidal terms. So we were looking for a tidal imprint in the gravitational wave signal to say, that was a neutron star. However, unfortunately, this system is too asymmetric and too massive for us to actually be able to tell that. So there's no way that we can tell from tidal effects whether that secondary object is a neutron star. Now, we've kind of gone through various kind of different scenarios, and really right now, the most likely scenario is that secondary object is a really light black hole. That's just basically where the data is kind of pointing us towards. But it's pointing that GW190814 was formed in a very different environment to a lot of our other black holes to be able to create such an asymmetric system. So for instance, it could have formed in, say, a young dense star cluster or disks around active galactic nuclei. They seem like some of the most promising hosts, but again, this object seems a little bit different and a little bit weird. On the bottom left there, you're seeing the most likely mass of that secondary object through different lenses for approximation of what our gravitational waves might be. So on the x-axis being there, the primary mass, and on the y-axis there, the secondary mass. And you can see from these two slightly different waveform families, so the slightly different signatures of the gravitational wave that we used, that they're coming out at pretty something similar. And either way, the mass is firmly coming in around the mass gap region. So again, this one is still out. We're still not too sure fully what's going on here. Still exciting. And now we've got another binary neutron star system just to point out to you. This is GW190425. So this happened only 25 days into the run. Now, this is the second binary neutron star system that we had seen. Now, there's no electromagnetic counterparts as such that I think anybody has detected. And that's just because one of our detectors was offline. So the sky localization was really quite bad. It was really quite large. So the masses of these objects, the primary being stated up there and the secondary, again, just on the screen there. So if you like, individually, those masses aren't too exciting. They're around, if you like, the maximum mass of, or lower of what known neutron stars are from EM observations. But actually, it's when you look at the total mass of this system that things get interesting. So the total mass of this system is something like 3.3 to 3.7 solar masses. This is when you combine the two masses of the neutron stars. And we don't have a binary of neutron stars that heavy in the galaxy. So that's exciting. That's interesting to know. Like, what is it? Like, how did this form very different to neutron star binaries that's very different than what our galaxy is seeing? And the bottom right plot there is just showing you a little bit more understanding about that. So the the x-axis is there showing you the total mass of the system, and on the y there probability density. The grey region is showing you individual binary neutron star systems in the galaxy, and the dashed line there showing you, if you like, the average of all of them put together. The orange and the blue curves, if you like, are from this one event, trying to understand, if you like, what the spin features of that event are. Now, if the spin features of GW190425 are small, like all of the neutron star binaries that we've seen, you want to look at the orange curve. Whereas if you want to let, if you like, it spin really quite maximally, it's the blue curve. But either way, what we're seeing is it's a system that is very, very different to what we are actually seeing within the galaxy. So now I want to move on to talking about the black hole mass distribution. So we started to see something like 50 events right now. So let's try and to understand what is it that we're actually seeing. So what we did here is that we took 47 out of 50 of our events to actually try to model and try to understand. 47 just because they have false alarm rates of less than 1 per year. So we're super, super confident that they're gravitational waves. And what we do is we model the primary mass of the binary like one of the distributions that you're seeing here in the pictures. So on the far left there is a very simple model where the distribution might follow a power law with hard cutoff and a lower and an upper mass. The second distribution here, a broken power law distribution, quite simply the lower mass has been smoothed to avoid a hard cutoff, and we've allowed for a break in the power law at some mass. And this might give an idea of a buildup of a population of black holes at a specific mass. The third is, again, a slightly more complicated distribution, building on from the second, but instead of just allowing for a mass break, we allow for a Gaussian peak, again, to model the potential pileup of pulsation of black holes from pulsation pair instability supernovae. And the fourth model that we allow our data to see if it fits allows for a second Gaussian peak, which might indicate black holes that are within the mass gap region, but due to previous mergers or hierarchical merger scenario. So we tried to fit our data to these 4 different distributions. And this is what we were seeing. So on the x-axis are the primary masses of the compact objects, and on the y is, if you like, the rate with the mass. Solid lines are showing you the posterior distribution, which is being averaged over model uncertainties, the shaded regions being 90% credible regions, and the grey bands, the 90% credible bound on if there is a location for a feature, such as a break or a peak. Now, you can't see it extremely well from this figure, sorry. But what we find is the truncated power law, i.e. the simplest model, does not fit with our data. It doesn't seem to fit at all with the high mass binary black hole events that we have found. But we are finding that the other 3 models are consistent with our data so far. But we're finding that all these 3 models seem to pick out a feature at around 37 solar masses, and that the slope, the power law, seems to follow an index between 2 and 2.7. So just to kind of sum up some of the key findings then. So there seems to be some strong statistical evidence that the model for the black hole mass distribution has a peak or tapering of some kind with a feature around 37 solar masses, which may indicate a buildup of black hole masses due to pair instability supernovae. We found that 97% of our binary black hole systems have a primary mass below 45 solar masses as well. We do observe a lack of systems between the black hole and between the neutron star and the black hole mass gap. And we seem to see a turnover in the spectrum at about 8 solar masses. We do, however, find that the minimum mass of the black holes in binary black hole systems are below 6.6 solar masses. And these are greater than the masses of black hole candidates in galactic binaries. And we still find that 190814, that really asymmetric system, doesn't really fit very well with the population. It seems to indicate it's part of a secondary, a slightly different population. But again, this is all findings from 47 binary black hole systems so far. Now let's look at the spin distribution of our system. So we like to look at the spins to try and understand, see if we can glean a bit of an idea about the environments in which our binary is formed. So one thing that we do look at is something called chi effective, which is really understanding how the merger is sped up or slowed down due to the black hole's spin being aligned to the orbital angular momentum. So most spins of our black holes seem to be aligned with the orbital angular momentum, which indicates that the black hole's formed in the field. So i.e. in isolation, supernova black hole, or some combination thereof. And the spins are pointing nicely upwards or maybe downwards, but either way, aligned with each other. However, between 2 and 50% of our black holes seem to have anti-aligned spins, which indicates that they were being formed in dynamically merged scenario, so potentially somewhere that is really quite a really quite dense region, such as say a globular cluster or something like that. On the left-hand side, what you can see here is a probability density function for the chi effective for all of our events, and what you can see is obviously the chi effective there nicely follows a very Gaussian distribution, quite around 0. So again, it's supporting what I'm currently saying in terms of being formed in the field versus in say globular clusters or something like that. And at the moment, we don't have enough evidence based on the mass distribution and the spin distributions to say for certain whether we're seeing hierarchical mergers just yet. We need more events. However, based on these 47 events that we've kind of combined, what we are seeing is based on the population, there is evidence of spin-induced precession in the orbital plane. No individual event exhibits precession, but when you look at all the 47 events together, all the data are preferring models that include precession. So that's really quite nice and exciting to see. Rates. So what does this mean for the number of mergers with respect to redshift? That's what you're seeing there in the plot on the right-hand side. Rate on the Y, redshift on the X. So the rate of binary neutron star mergers is currently something around 320 per gigaparsec cubed per year, and binary black holes 24 per gigaparsec cubed per year. Sorry, that's my fault with the notation of the gigaparsecs there. So what we've been trying to understand is our rate, following what we're expecting from star formation rate? Are we following what the stars are doing? And right now, our data is inconclusive. As you might expect, we don't have enough events so far, but the data are both consistent with the rate being constant in time, as well as tracking the star formation rate in the local universe. And that's what you're seeing there on the right-hand side. So the dark blue line is showing, if you like, one of our rate distribution in redshift, and the dashed line is showing you the shape of the star formation rate in the local universe. So if you like, the data right now is preferring something between a constant rate and tracking the star formation rate. But I think we'll know more with more time and more events. But it's quite interesting, really, that when you look at the merger rate of the binary black holes at a redshift of 1, divide it with the merger rate of the redshift of 0, we find that there's a factor difference of about 2.5. If you do the exact same with the star formation rate, you get a factor of about 6. Now, right now, it's still within errors lining up, but yeah, it's quite interesting to note right now that, you know, I can't say for certain, are we following the star formation rate? Maybe. Only time will tell. I think we'll have to wait for more and more events to kind of come out from here. And we also tested all of our events against general relativity. Is Einstein still coming out on top? So what we do is we do a number of different things, which I don't unfortunately have time to go into, but we, if you like, can assume some deviation in general relativity and test to see if the data prefers that. Nope, it still prefers GR. We can also look to see whether details of the inspiral of the binary black holes match up with what we can infer from the ring down signal. Again, it follows everything that GR says. Everything right now is pointing towards GR. Put it this way, we've not found we've found no evidence that there's other forms of gravity that fit the data. GR is still fitting all of our data exceptionally well. We also looked at the gravitational wave dispersion and found that the graviton mass must be below 1.76 times 10⁻23 electron volts per speed of light squared. And so this is a slight improvement on what we have previously said. And again, we find no evidence of gravitational wave from echoes or binary or black hole mimickers. Very sorry just to kind of put that information out there and not go into more detail, but there is a nice paper on the archive released only yesterday if you want to learn more about it. And something else always to point out is that whenever we release events, we release also the data around the events. So the Gravitational Wave Open Science Center houses all of our data. All of our 1, all of our 2 data exists, and right now all the data around O3A events exist there. And so there's some really nice notebooks and things like that for you to go in and learn to play with our data, and then do what you like with it. Go and find more black holes, hopefully, or if you like, reconfirm what it is that we've already seen. But the data is out there in case you'd like to do something with it. So just to finish up, where are we now? We're massively in the throes of still understanding what is in O3b. So O3b started in November 2019 and then concluded in March of this year. Unfortunately, it was cut short by about a month due to the COVID pandemic. So we still have quite a few months of data still to go through and much more gravitational wave signals to discover. Now, in terms of what this means in the general gravitational wave landscape, or if you like, ground-based gravitational wave landscape, this is where we are right now. This is a plot from what we call the observing scenarios document for the LIGO, Virgo, Cagra detectors over the next 5 years or so. The red line is nicely showing you where we are right now. They're almost approaching the 2021 scenario. So right now, all of our interferometers are offline and going through major upgrades to, hopefully turn on at design sensitivity in the 04 observing runs, which right now will not start before spring of 2022. We're going to have a complete year off at least. Things have obviously been put back to recent scenarios, which I'm sure you can appreciate. We'll then be online for on the order of a year. We'll then go offline, do further upgrades to then what will be called the A+ era, whereby we hope to double sensitivity again, LIGO India to come online, and then something around the 2025 region to be able to go after even more gravitational wave sources in the local universe. So ground-based interferometers, this is the rough prospect over the next 5 to 6 years. Beyond that, we are looking at the 3G detectors, such as the Einstein telescope or cosmic explorers. This is going to be hopefully happening in the 2030s or so. Einstein telescope will be a European-based interferometer. It's right now either going to be in Sardinia or between the Netherlands, Belgian, and German borders around Maastricht area, something like that, perhaps. And what we hope to do here is put an interferometer with 10-kilometer arms underground and reduce the sensitivity. Increase the sensitivity, but reduce the frequency at which we can see gravitational waves down to 1 Hertz. And this will help us to be able to explore black hole seeds, for instance. At the same time, the American detector, Cosmic Explorer, will be something like a 40-kilometer instrument with sensitivity very similar to, if you like, sensitivity frequency band, similar to what the current ground-based detectors are, starting around the 10 Hertz region. But we need both of these to come online at the same time so we can work collaboratively to go after those if you like, all of the black hole types that we can kind of see in the visible universe. I always do like that tagline for Cosmic Explorer. It will see all GW190814, so that's the very first detection of gravitational wave, like black hole mergers in the visible universe. So it's an extremely exciting time when those interferometers do come online. 15, 20 years, I guess 15 years time frame is probably the best thing to think about that one. As well, there's the LISA experiment, which is hopefully going to be launched in the early 2030s. And LISA will be very complementary to the ground-based interferometers because it's going to be looking for gravitational waves at a slightly lower frequency range. And so it will be able to see out to a redshift of something like 20 and see the very first black holes forming. All the key technologies have been demonstrated, and we're right now building up to trying to be ready for when LISA actually launches, and after going after those supermassive black hole collisions, as well as all the kind of other really exciting things to go after. So as always, I'll end here, and really just to point out that the ground-based interferometers have only unlocked right now the millisecond region of the gravitational wave spectrum. There's still the minutes, the years to decades, and billions of years to kind of go after. LISA will open up the minutes to hours long gravitational waves. Hopefully pulsar timing arrays won't be too long off at the moment, finding gravitational waves that are either years to decades in length, and maybe something like another microwave experiment will be able to find gravitational waves from the very early universe. But yeah, we know about the electromagnetic spectrum. We have only just started unlocking the gravitational wave spectrum. So this is a really exciting time to see what comes out of gravitational waves. So thank you.
Wow, Laura, thank you very much. It was a very series of very exciting results and a really nice talk. So I'll say thank you on behalf of everyone, because clapping is tough virtually. So I imagine there'll be quite a few questions. Who would like to go first?
Can I ask a question?
Yes, sure, of course.
Laura, thank you for a very exciting talk. And of course, we're very lucky to have it just the day after the exciting announcements. Maybe Ed foresaw that, I don't know. But I just want to make a comment, which is that you focus on some of these anomalous events, and in particular the event which involves very high mass black holes, and the event which involves the black hole in the low mass gap. And I just wanted to plug that the other popular explanation in certain quarters, at least, is that the black holes, some of those black holes are of primordial origin, because that does naturally produce black holes in the high mass range, and it also produces black holes in the mass gap where you don't get them from normal stellar evolution. And although I know this isn't the mainstream view among, the LIGO people themselves, there's still quite a large number of people who are looking at this proposal, and because it has rather clean predictions as to what the mass distribution is and what the spin distribution is, and actually I'm a bit biased because I've worked on the subject for so many years, but I think it's looking rather good at the moment for the PBH scenario. But I just wanted to plug that because you didn't mention it.
No, absolutely. And thank you very much for doing that. The papers go into so much more detail than I do, and I think that they do mention it, and rightly so.
Thank you.
Tessa, I think you were next.
Hi, thanks for a fantastic talk, Laura. I also wanted to ask about the high mass event, and I've forgotten the number, whatever it is now.
190521. Ah.
Okay, I need to. It's too hard to memorize all the numbers.
Absolutely.
And you talked about the possibility of this, there being like a previous merger that formed one of these, and then another, sort of being cumulative series of mergers. And I wondered does that tell you anything about the host galaxy of this kind of event, that it had to be, as you say, dense enough and around long enough for this kind of thing to happen, and if that could be used to try and pin down potential host galaxies?
That's really interesting. I hadn't thought about that. I would hope so in some respects. Now, this event, because it's so high mass, it's obviously quite far away. And I think that, if you like, the volume of the universe in which it came from contains a crazy number of galaxies. So I don't think it can be used at the moment, if you like, to constrain within that volume which galaxy it came from. But at the other spectrum thing, if you knew exactly what every single galaxy feature in that region was, I assume, why can't you just say, well, that one's not not dense enough, that one's not dense enough, and work it out like that. So I still think there'd be a lot of them, if you like, within that volume. But certainly, I think that sounds like a great idea, and I'm sure people are thinking about that. Well, I hope they are anyway, but not in LIGO Virgo. This is for the rest of the community to be pondering.
Okay, great. Because for this sort of dark sirens idea, the idea that we won't have that many EM counterparts, anything that could be helped to throw out half the galaxies or something would at least be some improvement.
Yeah, no, definitely, absolutely. I don't think that I'll say that in LIGO Virgo, obviously we're doing a calculation for that. I don't think we're doing anything like that, but that totally makes sense if somebody else is doing that. Like I know that like the Dark Energy Survey and some other people are looking for, say, what H0 is and various things like that. So yeah, that totally makes a lot of sense.
Okay, thanks.
Sasha?
Yeah. My question is, when you mentioned about spin and aligned with orbital or inverse, so how is it possible? My question is it possible to somehow relate the spin information with models, whether they form from multiple merging one by one black holes, or with, as Bernd mentioned, with primordial black holes. And as I understand, the rest is when black holes are formed in binaries. So is it possible to relate it more reliable, and is it reasonable to walk in this direction? What do you think?
Right. So right now, spins are a little bit hard for us to detect. Individual spins, let's say, of which mass and things like that. Like we can measure the effective spin, chi-effective here, which is a combination of the masses. Sorry, a combination of the spins weighted with the masses. We can measure that fairly well, but disentangling the individual spins is still a little bit hard for us to do. So we're starting to get a bit of an idea about, if you like, what the spin distribution of our various systems are. And right now, we can't say for certain if we are seeing hierarchical mergers. I think we're not far off being able to say for certain one way or the other. We just need more events, I think, really. We just need the population to get a little bit bigger. I hope we can do the exact same for understanding, if you like, whether things are being formed in the field from the primordial side of things or whether they're being formed dynamically. But right now, we're still very much treading lightly and not saying for certain, if you like. We're not staking, we're not putting all our eggs in one basket yet.
So, roughly speaking, how many other sources should be discovered in order to make some statistical conclusions about it? Just roughly, very roughly, 1,000, 2,000 or what?
I don't think that many. I think you need a few hundred at least.
Okay, thank you very much.
I would hope by the end of the next observing run, so by the end of '04, with the event rate that we're expecting, to be able to say something more. So what would that be? 2022, 2023. So by about 2024, we should be able to, I'd hope that we could say something.
Okay, thank you very much. Thank you for talk and for answers to questions.
Okay, are there any other, Tessa, do you have another question, or is it still up from before?
No, I do have more questions.
Okay, yep, great.
If anyone else wants to chip in. Laura, when you were talking about you were trying to constrain the rate.
Yeah.
And you showed us a plot where you tried to ask, is it constant with time, or does it trace star formation? And the data seemed to kind of be somewhere in the middle. Are there any other mainstream possibilities that are considered to correlate with the rate?
I don't know, actually. From what I can remember of what we've done, I think we just kind of kept it simple. These are our rates. It kind of follows the star formation rate, kind of not. But I think we're putting this information over the fence so others can come and tell us what it might be actually looking like. I would always say that we're very good at detection and we've got some astrophysics down, but we need the rest of the community to weigh in here.
Okay. All right, lots to do then.
Oh yeah, definitely.
I mean, Laura, can I follow up that question? I mean, if you had a scenario where it was an earlier generation of black holes, in other words, not associated with star formation, I guess the most natural prediction would be that it would simply be a constant rate.
Right.
You know, because whatever the initial distribution of the separations was, that would give you the rate, but then it would have nothing to do with the star formation rate. So looking at your diagram, would a person who was keen on that scenario want to get the constant in time solution?
I think that sounds plausible. I think that sounds like the right way around to me. I don't know if we purposely say, I'd have to read paper again whether we purposely, like say, constant equals primordial and things like that. I don't know if we spell it out in so many words, but right now the data seems to be somewhere between the two. And yeah, unfortunately, more events before we can say whether, I guess, like you said, if it is flat, that it is kind of favoring the scenario that you're mentioning.
Well, actually, it wouldn't necessarily be constant. It would depend on the distribution of the separations of the initial black holes.
Right.
And they may either form at an early stage, or they might form later on, and after galaxy formation. So it's the distribution of the separations which would determine what the actual rate was. But anyway, it's a very interesting graph.
Bill, and I'm not too sure exactly what it is that you work on, but I might conjecture you to run various simulations of various separations, and can you work out what the rate distribution would be and how well it might match the data? That would be great for I think all of us to learn more.
Yeah.
Okay, I actually had a question as well, so I'll use the chair's prerogative. You're talking about the sort of earlier in the talk, talking about sort of the low latency search sort of in real time that would allow the sort of electromagnetic observers to sort of point pretty soon after, I guess, within a couple of minutes of the merger. Then a high latency search that was sort of a bit more detailed because you knew a lot more about the data. I was wondering whether there are plans to kind of take the lessons that you would learn from a high latency search and then apply them to future low latency searches on the next sort of 03B kind of onwards. And then what that might kind of help in terms of the sensitivity, and then what the electromagnetic wave observations would be able to add to this picture.
Yeah, so something I neglected to mention is one of the main reasons that I'm trying to think how best to describe this. There's a lot of techniques in the high latency search that just take time, is basically one of the big problems that we've got. So by that point, everybody with a telescope already wants to know about it and be pointing. So some things we can't just put in. No, we are, like you said, we've taken a lot of lessons learned from the last observing run. I was actually in a discussion about that yesterday, and we're trying to think, like you said, of what we can incorporate. So for instance, some data quality information, i.e., some rubbish in the data. Is it a glitch? Is it an event? If you like, almost an aspect of that step came after the detection. Now, one thing we want to do is kind of fold some information in about the detector and take that into the searches before they claim a detection. So something like that might nicely help out with, if you like, the retraction rate, fingers crossed, in 04, let's say. There's other things that people are working on, for instance, if you like a low latency search, whereby we might be able to pick up the Inspiral earlier. So for instance, we might be able to find the binary neutron star maybe a minute before it merged, to give you the extra time. With that, the earlier you detect, the if you like, the less sensitive you are, and as you build up, as you bring in more signal, if you like, the sky localization will just kind of shrink down. So there is that kind of like trade-off to be going after. But yeah, that's one thing. That's another thing. But with the 04 observation run, we expect CAGRA to also be operational, which will help with localization being on the other side of the world, to say Virgo and the United States. So with more separation of interferometers, more time delays, then we can hopefully hone in a bit better about signals and things like that.
Cool. Yeah, and that would be nice. So what exactly does the electromagnetic sort of wave observations kind of tell you, and how sensitive is that to sort of the time after the merger?
Yeah, so it totally depends on what you're kind of seeing, but right now, at least from previous observations, the collision of neutron stars, and we conjecture some black hole neutron stars, black holes not too large, should create, for instance, a short gamma ray burst. That comes very, very soon after the gravitational wave. So if you like, there's no way we can point a Fermi or a Swift. They'll have already figured out that something's come through by the time we figured something's come through. But it's all about trying to tell optical and near infrared to point at a very specific galaxy if we can do. Don't think we'll be able to get down to that kind of resolution, but at least, point to so many tens of square degrees and say, look for the kilonova signature. So a kilonova, what's it called now? So it's a an isotropic thermal emission from neutron star matter that's been flung together and then decaying to stability. And so we expect that to be there for a number of events. So that's what the majority, I think, of telescopes are going after. So that can obviously give you a bit of information about what the objects were that created it, and obviously that tells you the elemental composition and things like that. And we could do a H0 calculation in a really nice way because we know exactly which host galaxy it will come from. But nicely, if you carry on and you wait for the some of the longer signals, such as like I think some of the X-ray signals and some of the radio signals, I think I've got that right way around. That can tell you something about the remnant, what created it. So with GW190814, sorry everybody, I just know all the numbers in my mind. That's the first binary neutron star merger that we detected in 2017. We couldn't tell for certain, if you like, what the final object was. We know two neutron stars collided, and we think that it went to a black hole. We can't say for certain because unfortunately where the signal is residing is in a not very sensitive region for a gravitational wave interferometer. But the question is, did it go straight to a black hole? Did it go to a long-lived remnant of a neutron star? Did it go to a hypermassive kind of spinning neutron star? We're not quite sure now. As we become more sensitive, we will hopefully be able to go after that form of signal. But in some really nice papers that came out after the observation of that event, various astronomers came back with, right, well, we think it was a long-lived remnant of a neutron star that then collapsed to a black hole because we saw these signals. So, you know, so by observing like various things of those signals, it can tell you much more about, if you like, with the remnant of what it went to, and then, yeah, that type of thing.
Yeah, very cool. Okay, does anyone have any final questions for Laura? Okay, in which case, then we're going to sort of try, as I kind of mentioned in the email, we're going to try out a bit of a kind of a social breakout room kind of